Next, we need to discuss the logic behind randomized comparative experiments. So, random assignments of subjects form groups that should be similar in all respects before the treatments are applied. And then a comparative experiment with randomization ensures that influences other than experimental treatment operate equally on the groups, right? Like any outside factors. Differences in average response must be due either to treatments or to the play of chance in the random assignments of subjects to the treatment groups. So here are some principles of experimental design. So the basic principles of statistical design are control. You need to restrict the effects of lurking variables on response, most simply by comparing two or more treatments. This is really, really important. Randomization. You need to use chance to assign subjects to the treatments. Replication. Studies need to be replicable. And you need to make sure you use enough subjects in each group to reduce the variation in the test results. An observed effect so large that would rarely occur by chance is called statistically significant, right? We want to see, you hope in your studies that you're conducting, you hope that they are statistically significant. But it's also important to know that a statistically significant association in data does not imply causation. Facts are facts. We also need to be aware of confounding, right? Confounding can happen in experiments. A lurking variable is a variable that is not among the explanatory or response variables in a study, and they may influence the response variable. I feel like I've talked about confounding before in earlier videos. Two variables are confounded when their effects on a response variable cannot be distinguished from each other, right? If I've got an explanatory variable and a lurking variable and we can't distinguish them, that's when we have confounding. Observational studies of the effect of one variable on another often fail because of confounding between the explanatory variable and one or more lurking variables. You can't have multiple lurking variables. Well, design experiments take steps to avoid confounding. So here are two common types of confounding: placebo effect and experimenter effect. So placebo effect refers to a situation in which patients improve simply because they believe they're receiving a useful treatment, right? Like when you're little and you hurt yourself and your mom's like, oh, let me kiss it better. That's a placebo effect. It's not actually healing you. I wish it was. So then there's experimenter effect, right? The experimenter somehow influences the results. This can occur when experimenters know which participants are in the treatment and control groups. This is bad. And the only way to avoid experimenter effect is to make sure the experimenters don't know which subjects are in which groups. And for that, we need blinding. So blinding experiments. Single blinding is if the participants don't know whether they are members of the treatment or control group. All experiments should be single blind. Like you never want your participants to know whether they're getting a real treatment or a placebo. That would ruin the point of your experiment. A double blind experiment is if neither the participants nor the experimenters know who belongs to the treatment group and who belongs to the control group. So, for example, 2, for each of the following experiments described below, identify any problems and explain how the problems could be avoided. So, a new drug for ADHD is supposed to make affected children more polite. Randomly selected children suffering from ADHD are divided into treatment groups and control groups. This experiment is single blind, meaning the experimenters know who's getting a real treatment and who's not. Experimenters evaluate how polite the children are during one-on-one interviews. So this has a lot of problems. First, it should definitely not be single blind. It should be double blind, right? Polite is subjective. Also, if they know students who's in the group that actually got the treatment, they could talk to them more gently during those one-on-one interviews, or automatically just rate them polite because they think they should be because they're getting the drug. So this has a lot of problems, but it could be fixed by double blinding. Second, a chiropractor performs adjustments on 25 patients with back pain. Afterward, 18 of the patients say they feel better. He concludes that the adjustments are an effective treatment. So, first off, he did this himself on his 25 patients. 18 of them tell him, the one who just done the job, that they feel better, right? You might feel bad. Like, it's like when someone makes you dinner and they're like, oh, how's dinner? And always you're like, great. Even if it's not like so great, you're always like, oh my gosh, this is so good, because you're being polite, right? So this is not the greatest way to conduct an experiment. We definitely need some double blinding going on here. Next, let's talk about matched pairs. So the idea of this experimental design is to create or use matching pairs of similar experimental units for comparing two treatments. So a matched pair design is a randomized experimental design in which within each matching pair of similar subjects, chance is used to determine which subject gets a treatment. Sometimes a pair in a matched pair design consists of a single unit that receives both treatments because the order of the treatments can influence the response. Chance is then used to determine which treatment is applied for each unit. There's also block design when it comes to experiments. So these matched pairs are one kind of block design. Each pair would form a block. And a block is a group of individuals that are known before the experiment to do similar in some way that is expected to affect their response to treatment, right? So again, controlling for outside variables. In block design, the random assignment of experimental units to treatments is carried out separately within each block. So a wise experimenter will form blocks based on the most important unavoidable sources of variability among the subjects. And then randomization will then average out the effects of the remaining lurking variables and allow unbiased comparison of the treatments. That's our goal. So here we have an illustration of block design. So we've got our subject. We break our subjects up into two groups. The blocks, not random. Then we randomly assign them to groups, and then we can compare their reactions.